All right, are we live? Hello, 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 hello. Just take a moment here before I get going. So I looked at this problem the other day, and I was also kind of in like the throes of my own. I deleted the video from the other day, but yeah, I was in the throes of my own. I don't know, mind, I guess, my own thoughts, and yeah. So let's go ahead and not continue, but kind of continue where we left off. You've seen this video, you won't have any context. So basically, I didn't really get very far. I basically was just thinking about a problem. I didn't get very far. I was basically thinking about a problem that. Let me lower the volume a little bit here because I'm going to be speaking. It's okay. All right, we'll just leave it. I didn't get very far, and I didn't get very far, and spending like hours messing around with different possible solutions. None of them were correct. So I think what I should do is think about a correct solution, not what I'm doing here. Like, there's this thing you could do where like you try to code something that's not correct, and there's a million things that aren't correct. So it could take you a very long time. You just keep programming things over and over again that aren't correct. Like, you're better off getting something that's correct and then trying to code that. Right, the coding is usually not really the problem. The problem is usually the programming is usually not the problem. The problem is usually actually the solution. So we need to spend more time thinking about the solution, right? Now, what also can happen, what makes this problem, this particular thing I'm describing, even more challenging, not only can you have a million different things that are wrong, and so programming all those things, wrong things, will take you a really long time, so you really should just want to focus on the thing that's right. You can have problems where you don't actually know what the optimal runtime is for the solution. And so even though you have a relatively good solution, you might think that there's possibly a better solution that actually isn't possible, and you don't necessarily know how to prove that it's not possible to do better than that. So now you're trying to spend a lot of time trying to find something that's not possible, programming a lot of wrong solutions. So that, I think it takes a little bit of humility. That, like, it's kind of weird. Could you imagine that the character of a person could influence how efficient they are as a programmer? Prideful programmer always fails. I don't know. That's a weird kind of philosophical thing to ponder, but maybe for another time. So I think that might be a situation I'm in here where I think if I found a quadratic time solution, that would be sufficient to solve the problem. And then I could probably check the discussion to find out that, like, yeah, that's probably about as well as you could do. There probably might be like a way to show that you can't actually do better than that. So we're going to try to go for something that's not particularly efficient, more efficient than like exponential time, but not too efficient, I guess, because it looks like I'm going to be sitting here thinking about this for a long time, trying to find something more efficient. And the thing about that's crazy is that if you can't prove it's not possible, then there's a chance that you just haven't thought up the more efficient solution, and you'll be kind of sad for spending a lot of time trying to think of that. Just kind of conjure it up, which is definitely, oh, that's a goofy face. Okay, anyway. Yeah, so let's think about how we can solve this problem. Let's think about it. Spend that time. Let's do it that way. A lot of likes on this too, which is kind of interesting to me. I kind of wasn't expecting that, but this is a really interesting question, nonetheless. You are given an array of people, which are the attributes of some people in a queue, not necessarily in order. Each people of I is going to have an h and a k value, representing the ith person of height h sub I with exactly k sub I. Other people in front who have a height greater than or equal to h sub I. Reconstruct and return the queue that is represented by the input array people. The returned queue should be formatted as an array q, where q of j is h of j, h of k of j, is the attribute of the jth person in the queue. Q of 0 is the person at the front of the queue. So the first time I read this, like, my reading comprehension was just shot. Like, I was like, I have no idea what they're talking about. Then they gave an example and it made some sense. So basically, this sequence here is rearranged into this sequence because there's 0 people in front of 5 that have 5 or higher height. There are 0 people in front of 7, which is just 5, that have height 7 or higher. But in front of this guy, there's 2 people in the queue, 5, 5, 2, where 5 is at least 5 and 7 is at least 5. So there's 2 people in front. 6, 1, similar thing. There's at least 1 that's in front. 4, 4, there's at least 4 in front. There's actually exactly 4. Excuse me. There's exactly 4 that have at least that height. 1, 2, 3, 4, and then for 7, 1, there's exactly 1 to the left that has at least height 7. That's sort of what basically rearrange these elements in the queue such that those conditions hold. That's sort of what what's being asked. And yeah, I mean, there's at least one solution that I can think of that I'm thinking of just coding that and seeing how it goes. Basically a backtracking solution where you pretty much iterate through all of the permutations, and then each time that a permutation doesn't work, then you would sort of stop there, you terminate early and backtrack. That's kind of how I'm going to look to do it, I suppose. I could code that up and just see how fast it is. The problem is that it should be exponential time, and 2000 is kind of a lot for something that's exponential. Like, even sort of an efficient exponential time algorithm is still going to be pretty slow with 2000 elements. So I'm not sure if, I guess that's entirely possible, something like that, to do it that way. Or it's not going to be efficient enough. I think also the way I was thinking about doing it is select an element, or yes, you basically would change you would have a set of like possible things to choose from, and the way I would maintain that set efficiently is that I would like at each recursive step. So with backtracking questions, you basically have like a state change, call the recursive function, and then undo that state change. And what I was thinking is that you would sort of have like, okay, you have a set of things to pick from, and you're going to iterate over each possible selection. And so the state change at each selection is going to be to swap. It's probably easier to swap this element with the back, this first element, and then pop it off. And that would be selected that element, and the thing that's tricky about that, yeah, that's fine. That should be okay. You pop it off, swap it with the back element, then pop that, and then when you recurse, you sort of recurse over what's left in that set, those possible choices, and you kind of do that at each step. And then when you undo that state change, you would remember what you had swapped, where you swapped it, and then you would push back the same element to the back and then swap again, so it would return to the state that was changed. And then inductively, right, or recursively, if the state's always back to what it was before, then that shouldn't be an issue. That should work fine. And then what you would do at each step is you do a check to see if all of the elements are. Now, I guess my question is, I guess you would build an output array. So you'd push that element onto the back of this, the one you selected, and then you would, when you recurse, you do a check to see if the last element you added is satisfied. And then if it's not, it's really two checks. If the last element you satisfied is correct, if it's not, then you would return early. and then if it is correct, that passes that check. And the second check is to see if you have all the elements sort of picked, and then you return. I want to say I actually think that I think the backtracking solution with pruning, like that's basically gets pruned. I want to say that that actually would be pretty efficient. Like it might actually be sufficient for this question, which would be kind of upsetting to me because that's like kind of easy to program. That would be like pretty quick to realize, think about, code it. But here I am, I spent like 3.5 hours thinking about this problem, trying to come up with something more efficient than that. I want to say we could at least try something that's quadratic time. I think something that's quadratic time could and should be efficient. However, I don't really have an idea for something that would be quadratic time. I really don't know. I guess it would be something like you would pick the, let's do the second input too. Let's try that. You would pick like the smallest element first and swap that. Of all these elements, the quote-unquote smallest would be the one with the smallest height, and then also of the elements of the smallest height, or not the smallest height, the smallest k value, and then of the elements of the smallest k value, also the, see, that's not really true either, right? That doesn't really work. Like I was thinking about like doing like a kind of like a bubble sort type of thing, where, and I guess you could do that. Maybe that's what you should do, is a modified bubble sort, where you compare 6 with 5. 5's condition fails, so you move 5 where 6 is, and then you compare 6 with 4. 4's condition fails, so you move 4 where 6 is. And you compare 6 and 3, and 6 with 3. 3 fails because of the other elements to the left, so now you move 6 with 3. Compare 6 with 2. 2 is failing, you move 2 over. 6 with 1 and 4. 1 and 4 is failing, so you move 4 over, 1 and 4 over. I want to say a modified bubble sort actually solves this problem. That's really interesting, but I think it does. And let's try that. That's got to be more efficient than the dude, that's wild. That's got to be more efficient than the backtracking solution. But the problem with using a modified bubble sort is it's not necessarily constant time. We have to find a way to, in constant time, to check this condition on each of these values. I guess and also is we assume at least one element is in the right spot. We don't necessarily know which element is in the right spot. Like we don't know, how does bubble sort even work? How does bubble sort even work? What does it do? It does n iterations until it's sorted. I want to say, I guess that's fine. I guess we could just start from the beginning every time. I guess it doesn't really matter. Yeah, we'll just do it n times for each element. We'll do just to do the bubbling that we just described. That if the element's not in the right spot, then move it to the yeah, swap the two elements. So okay, but how do we check that condition? Actually, I think if we can get the bubble sort to work correctly, then I think we can get any kind of sorting to work correctly, and then we should be able to do this very efficiently. Then we could actually do like a counting sort, or maybe not a counting sort with 1,000,000 values. Maybe a counting sort, I don't know. Could ponder that for some time. But let's see. So a bubble sort would be could run that on some test cases too to verify if that makes sense. How do we check that our condition is correct or not efficiently? We want to do that in constant time. Can keep track of the heights, I guess. The number of heights to the left, the number of heights to the right. Excuse me, I'm wondering if we could do a kind of a quick sort too. No, it doesn't really make sense. I don't know, man. I don't know. Let's just work on the bubble sort first. So, Can actually do a while loop where you just keep bubbling until all the elements are in the right spots. It's kind of what bubble sort does until every condition is satisfied. I think what we ought to do is if a condition is not satisfied, we shift it to the left. We swap it to the left. We bubble to the left. I think that's fine. But the problem with that is, how do we check these conditions efficiently? We can say at each index we want to have some kind of data structure that supports the query at a given index. How many elements to the left of our array is at least a certain height? How many elements to the left have a certain height? And when we swap elements, we want to modify that data structure accordingly, so that way it's efficient to make that query. So like a really simple approach would be, a naive approach would be to iterate from the left to that index, but not including that index, and count the values that are greater than that particular height. That's one approach. Another approach might be to actually use an interval tree, possibly, where we can sort of, I guess, keep track of the minimum height at each tree. At each node. And so when we want to query, we could say, yeah, maybe an interval tree would work. We would query, we would say, I gotta think about that. That's like kind of weird data structure. We would query and say, okay, the number of elements to the left is what would the query look like? It would be the minimum height of all the elements, right? So the minimum height of all the elements is a 1. That's sort of the head node. And then the left side and the right side, where there's a minimum on the left side and a minimum on the right side, I guess. And the minimum on the left side here is 4, so all three of those nodes are at least 4, and all the nodes on the right side. And I guess we could also keep track of how many of those nodes there are. 2. So then you could say, and I guess we would want to keep track of the index too. So we have an index and how many, I guess, of the indices. There's a starting and ending index for each node, as well as the minimum height. And so then when you query for some node that's larger, you want to actually look at the indices that are to the left of that particular index, the nodes, those particular nodes that are to the left. So like if you're looking for 0, 1, 2, 3, 4, the fourth index, the head node you wouldn't look at because it has everything. The left subtree, that left node you would look at, which we said the minimum height is 4. So actually 4 is greater than 2, so you would count all of those, and there's 3 of them. And then to the right side, you would say you have these all 3, which includes this node, which you don't want. So you wouldn't include that one. You would look at the children, and you would say, maybe there's 1 on the left and 2 on the right, or more likely 2 on the left and 1 on the right. You wouldn't look at the 1 on the right because that index is too large. Those indices are too large. You would recurse on the 1 on the left here. However, you wouldn't include. You would look at it again and say, okay, this index is in there, but we actually want only if all the indices are to the left. So then you would recurse on the 2 children, and you'd recur. Yeah, so you would. If all the indices are to the right, then you just ignore it. But the indices some of the indices are to the left, or if the indices are are greater than or equal to, if all the indices are greater than or equal to, then you ignore it. But if some of the indices are to the left, then you would recurse on the children. And so then you recurse on this child, and you see there's 1 node here. It's 1 node that's at least 3 of height 3, and so you would add that to your total query. And so now you know all the nodes to the left of this index are 1, 2, 3, 4 that are greater than or equal to 2. Yeah, so you could use an interval tree. You could use an interval tree to keep track, to in logarithmic time determine how many nodes, and obviously you would be swapping as you. Now the tricky thing here though is that you'd be modifying this interval tree as you go. So when you swap in values in these indices, you would, I guess, 2 things you're doing. You're removing. Actually, it's like 4 things you're doing. You're removing this 1 node and removing the other node, and then adding that both of those nodes back in. So the tricky thing about that is the modifying the heights of the nodes, I guess. I guess that's okay. Yeah, I guess you're just changing the height. So for the you would you have to find a way to update the interval tree appropriately, right? Given an index and a height, if you're changing that particular value. I got the querying, but the modifying, I still have to think about how would you do that. So you're actually not adding new nodes to the tree, which is great because that could really be challenging. But you can modify what's already in the tree, which should be fine. But how do we do that? At the root, you would be, let's say at a particular index you're changing the height, because that's kind of what we're doing. We're kind of doing 2 queries. We're changing the height of one. We're swapping 1 node with another, but we're changing the height of 1 index and the height of the other index. So yeah, let's say we swap 4, 0 with 2, 2, right? Swap these 2. So we're going to change the height at this index to 2 and the height at this index to 4. So first change the height at this index to 2, and we would say, I guess whichever node contains that index, we would want to update the minimum height. Yeah. So 4 is not greater than 1, so we don't change that. We check the left and check the right. The left contains this index, the right doesn't. Then we say, okay, modify that. So we're updating it to 2, right? So we're updating it to 2. So 2 is still greater than 1, so we don't touch the head node. The left node we do update to 2. And then I guess it would split into 6, 5, and 4, 0 on the left and the right. Then we don't touch the left node. We just return there because the index isn't there. But on the right side, we do have the index there. We update that to 2, and then that's the leaf node, and we're done. And then on the other side, we do the same thing for 4. So actually, updating shouldn't be a problem then. That should be also logarithmic time. So we could actually support that query relatively efficiently, right? Logarithmic time, and we can do the swapping. This is no problem, right? It's just two updates, one with the other. On the other, there's two different indices in the interval tree. So okay, we could do this bubble sort, which would take quadratic times log n time, which is kind of expensive, right? If we do log n of 2000, log base 2. Yeah, it's a factor of like 11 times slower. 40 million operations. It's kind of a lot of operations. Not to mention we still have to build the tree, which takes time. Yeah, it's kind of a lot of overhead that we're accruing here. Now the question is, can you use that interval tree to actually do this very efficiently, rather than, in other words, you could figure out which elements to swap and do it in n log n time rather than n squared log n time. Now that would be interesting, and I don't know. Let's see. Well, you could build the interval tree, and then I guess what you'd want to do is swap elements into the right spots so that their conditions are satisfied. So with 6, 0, the condition is satisfied. With 5, 0, condition is not satisfied with 6, 0 there. So we could swap 5 with 6 because you want the 0 elements to the left. So that would be satisfied if you move it to the first spot. And then is 6, 0 satisfied? It is. Is 4, 0 satisfied? It's not. So you don't want to swap that with 5. Move that to the front. So it's 4, 6, 5. Is 5 satisfied? It's not because of the 6. So you can move the 5 with the 6. So you have 4, 5, 6. 6 satisfied? It is. Is 3 satisfied? It's not because of the 4, 5, 6. So swap it with 6. Check 6 again. 6 is still satisfied. Check 2. 2 is not satisfied. Swap it with. Now, how do you figure out which node to swap it with? Well, you want 2 elements, right? So you can swap it 1, 2, right? Yeah, I guess I don't know. I guess you would swap it with the 3, 2 then. So you have the 3, 2. Swap 2, 2 with 3, 2. 3, 2 is now not in the right place. You swap that with the 6, 0. 6 is in the right place. Now 1, 4 doesn't work, right? 1, 2, 3, 4. So you swap that with the 6, 0. Is 6, 0 in the right place? It is. And then now they're all in the right spots. And technically you can go one by one and do, I don't know how many iterations you'd have to do at each spot, but if there's a constant number of iterations at each spot, then that would be n log n time. However, also that whole time you're listening to that extra noise being created by the headset. Let me lay down for a few minutes here. However, that if we could show it's a constant number of operations to move and find the right spot to put the element using the interval tree, then that's an efficient algorithm. Very efficient. However, a few problems here. One of them being, even though the update in the query that we were describing before is sufficient, is logarithmic, the problem you run into is you cannot necessarily answer. There's a few questions to answer. One, the query that is, where should this element go? The condition's not satisfied. We can answer that query, but then where should it go in the array in order to satisfy that condition? That query is not necessarily efficiently answered. And how many times do we need to check those two conditions, right? One is, okay, the value that's now at this index, where should it go? And is the condition satisfied? And where should it go if it's not? How many times do we have to answer those questions and swap elements until the condition is satisfied? That isn't necessarily, it's not necessarily clear how many times that gets called. Or it needs to be, evaluated, called. That could be more than constant time, and not only could it be more than constant time, it could be expensive, right? It could be actually like a linear number of operations, in which case we're kind of at a loss, even if the other answers are questions have been answered, right? If it's logarithmic to answer the prior query. So one of these queries is excuse me. All right, we said, so can we efficiently determine where this should go in the array in order to satisfy the condition? Well, maybe, I don't know. Okay, so we want the number of elements to the left that are smaller be, let's say for like 2, 2, right? Number of elements to the left that are smaller. Can we use the interval tree to answer this question? Maybe, I don't know. The head node tells us that all the nodes, the minimum is 1, and there's more than 2 nodes there. So we wouldn't want to put it to the right of that. Well, we have to actually find a particular index, right? So I guess we're looking for, the query is then a node, a leaf node that for which the number of elements to the left that are greater than a particular height is k, right? Or greater than or equal to a particular height is k. So I don't actually know how this query should go, but I'm assuming. So all the values of the minimum is a 1, and then I guess we would just recurse we would just operate on the left and the right, and say if the ones on the left are smaller, or excuse me, greater than or equal to, if the ones on the right are right, so we just recurse if the. Okay, I got it. So for that particular node, the head node, if the minimum is if the minimum is smaller than what we're looking for, then we are going to operate on the children, right? And so you'll operate on the left children, and you're going to, we'll just vaguely say operate on the children because there's something specific we want. But yeah, so you work on the left side, you work on the right side, and you say, on the left side, let's say there's 3 elements, but the largest value, this minimum value is 4. So now we know everything on the left side, there are values that are larger, and there's 3 of them. Okay, that's fine. We operate on the right side, and I guess we wouldn't recurse on the left side, I suppose, something like that. I would want to think about that for a second. The right side, we see the values are, the minimum is smaller than
than 2, and values are smaller than 2. And the problem, though, is the left side is so much larger that you wouldn't even bother considering the right side, because anything on the right side won't work. So we can kind of prune the right side at that point. Yeah, I want to say you would operate first on the left side, and then if there aren't enough values on the left side, then you'd operate on the right side. So it's kind of like a pre-order traversal, I guess. So okay, so you operate on the left side. Now operate on the left side. You have the left and right node now where the number of so I guess it could be organized as like 6050 on the left node and a left subtree, and 40 on the right subtree. We're looking to place 22. So the left side has 6050 already as 2, and once I guess that gives you the index immediately to the right. Once you have a height, or once you have a right, so the minimum height is 5, which is greater than 2. So you have I guess a number that you're looking for, and so you would take the element immediately to the right of that index, the rightmost index. Now, yeah, because that whole thing is going to be to the left. Right, I think that works. And so that would give you the index you're looking for. So you could query that in logarithmic time, where currently in the array, where things are currently, where you would want to put this element from left to right, where you could put it. And yeah, and then you would swap, and then you do the same thing again with the next element that you swapped with. And the question is how many. So yeah, I think you can answer that query efficiently. It would be. Excuse me. You could answer that query efficiently, but what would happen? You can answer that question if you can answer that question efficiently. In that case, excuse me. I guess it's actually you pick between the left subtree or the right subtree to iterate on. And you would say if the left subtree, if the height that you're looking at, the height that you're using for your query, if that height is larger than the minimum height shown on the left subtree, then you would actually want to recurse. If it's on the left subtree, if it's smaller, then you want to check the number of elements in the left subtree before recursing. If the number of elements exceeds the number you're looking for, then you've got to operate on the left subtree. If it's smaller, then you could skip the left subtree and go to the right subtree. Yeah, basically you're doing a logarithmic search on the particular index that you would want to pick, and you're using the interval tree to remove the elements. And I guess the head node is kind of like you just you always operate on the head node. Just thinking, because there's like a base case or something. There's like a base case that eventually you. I don't actually know. The algorithm's a little confusing. How would you do that? So. Yeah, usually the way that I set up my sort of recursive searches through trees is there's a base case and there's a left subtree recursion and a right subtree recursion, but each recursion kind of just takes a new tree. Each subtree is like a new tree. But this time you. It's a little bit strange, I guess, a little bit odd, because the head node actually you kind of always you don't really do anything with the head node. Like in all cases, you're gonna just kind of skip the head node and check the left subtree and the right subtree, because I guess the index to the right of the head node is always going to be like a non. Like not a possibility, I suppose, so something like that. I don't know. I don't really know how to say it, express it. Okay, maybe make that routine iterative rather than recursive. I think that makes a little more sense. Well, should be able to do both. It shouldn't matter. Should be able to do it recursively. It's kind of throwing me off because the head node is sort of like a sentinel node or a dummy node. You kind of just skip it every time. So how would this work? Okay. Looking for, what are you looking for? In the index of the tree, where to the left of that node, there are exactly k values that are greater than or equal to h. Okay, so you give it an h and a k value, and you get an index. And excuse me. Okay. So how do you know if you're a leaf node? Right. Okay. So you have to check if you're a leaf node or not. If you're, well, it doesn't matter actually. Just thinking. Yeah, you want to pick the index immediately to the right of that particular node. No. So the head node you'll never end up picking the head node by default. the reason that why you will never pick the head node is basically the node is if the number of values in the node are greater than or equal to the height, that's the return value. The number in the node, then you're going to pick if the number of elements in the node are greater than if the minimum height is greater than or equal to the height you're looking for, and the number of nodes in that node is equal to the number you're looking for also, which is k. So the minimum height's greater than or equal to h, and the number of nodes is equal to k. Then you're going to pick the index directly to the right of what's represented by that node. And you return that, and that's the base case. Or if it's an empty node or a null node, which is that you basically tried to operate in the children of a leaf. That is what you're after. That's if you're on operating on the left subtree. Now what's tricky about that approach, that'll skip the head node. What's tricky about that is you do want to also have a second number. I think that you're operating with piece of data or datum that is the number of nodes to the left that you've already seen that do have that height. So initially it'll be 0. However, but you're gonna add that too. You're gonna factor that in too. So it's not just the elements that are represented in that particular position, because you could be looking at a right subtree too, but also plus all the things you've seen on the left side already. Yeah, that's what I want to say. And basically, the head node will always have too many nodes in it that are greater than or equal to the target, because the target is in the full array, right? So you're always like one element larger, one element too many. So that'll always just get passed through. And then so you would operate on the left subtree, operate on the right subtree. After operating on the left subtree, you actually recursively you kind of want to return two values. You want to return how many you saw in the left subtree, how many values you found in the left subtree that are greater than or equal to h. And then you also want, now here's also another tricky thing. The value that you're about to move might be in a left subtree, and you're actually going to remove it from there, so it doesn't count towards its own. Now that's super confusing. What I would suggest is actually, I think, moving it to the rightmost position first, and then performing the search to figure out where it should go. So you perform one update to move it to the right in the array, and then you perform this algorithm to figure out where it should go, and then you'll do another update. So actually it kind of doubles all the time that you're spending, but I think that's the correct way to do it, because it won't work correctly otherwise. Because you'll be trying to figure out where that element should go when it's actually part of the equation, and it'll actually contribute to your results, I guess. It'll actually contribute to the calculation, which I think will actually throw off the calculation, right? Because if it's in the left side and we say, okay, we determine that there's one element in the left side, you're going to end up removing that element when you move it, and so the position that you pick actually won't have the right number of elements to the left. As confusing as that is, okay, let me think about that for a second. That's confusing. also makes me think that this problem might actually have a much simpler, more efficient solution too, because of this kind of property of like when you remove and add, how it kind of changes all of the calculations. But I digress. We'll just leave that in the fog for now. Leave that as uncertain. So, as I was saying, yeah, man, I'm pretty well stumped on this question. This is a challenging question. Using the interval tree, I mean, how do we manipulate this interval tree to kind of do what we want, support the functions we're looking for? Left subtree, we kind of want to know if this particular value, or excuse me, the H and K values unique. I think they have to be unique, the pairs, with respect to the values in the array, because if they're not unique, yeah, they can't be. They have to be unique, because if they're the same, the two nodes in the array in the queue are the same. That means the one to the right has the same height as the one to the left and has the same k as the one to the left, which means that there are k minus 1 nodes of at least height h to the left of the first node, and similarly that means that many nodes, and then yeah, k there are k nodes, there are k nodes of at least height h to the left of the first node, wherever that is, and then the second node, because it's to the right of that first node, has k plus 1 nodes of at least size h, because they both have the same height, which means that right node can never be placed properly. So these h and k values are always unique, which means, I guess that means that you could locate that where the node is currently in the interval tree and remove it from your calculations. So I guess you could instead of performing like multiple swap, an extra maneuver when you're looking at this index, the swap, you could just, excuse me, find the index of this node. Oh, suppose you already have the index of this node. You really should. Once you already have the index of this node, you just exclude it from the calculation. So any index that includes that particular index, you would just subtract the number of nodes. Yeah, we just subtract 1 from the number of nodes during your calculations. Yeah, do it that way. I think that's simple enough. That's a pretty simple modification you can make, so that way you can still do the same thing I was just describing. So what would you do? You would have a few different few pieces of data that would kind of slightly modify your search, but basically you're going to check the head node and say, okay, the number of nodes that we're considering, does it satisfy what we're looking for? If this index is included, we subtract 1. If the minimum height is larger, then we're going to perform a check. Further check that the number of values to the left or the number of nodes in this represented by this node, the number of nodes represented by this node's indices plus any accumulated nodes that we've seen, or accumulated indices that we've seen and then -1 if this node includes the value itself. If all of those check, then we want to put our new node to the right of this. To the index immediately to the right. Now we have to do one more check, and that's if this is the head node. We don't want to, excuse me, the root node of the entire tree. There's yet one more check to make sure we don't give a nonsensical index. Actually, in that case, I think what you would do is, excuse me. I want to say something like, if this node does, if you get the answer you're looking for, and this node is included in this index, I think you would actually take the furthest index to the right of that particular node. Otherwise, if it's not in there, then you would take the index one more, add 1. So add 1 for that return value, and then subtract 1 if the index that you're working with is included in this particular range. Something like that. A little bit confusing, but yeah, I think do it that way. Really, it's not if it's in the range. I think it's if it's to the left of that range. Yeah. Because that means that you've counted it. So really, it's just if it's to the left. This index is to the left of the rightmost node. In that case, you subtract 1. Interesting. Add 1 and subtract 1 from this node, the node that you're considering this largest index. That's the index you want to return. And also, same thing. That's how you perform the calculation on the number of nodes. That's okay. It's kind of a lot wrapped up in there, but that you perform that on every head. That's the base, sort of the base check. There's 2 checks. One check is if the node you're operating on, if it's null pointer, then you just return right there. You sort of terminate right there. And now the tricky thing is, and then the other one is what I just described, where you return the right index. But I want to say, how do you actually yeah, I mean, you could just make this void and modify a in other words, make the return value void and modify the an integer address to kind of make the set the return value that way. I think that's better, because the issue that you run into is use addresses for return values. I think it's better because of or use references for return values. I think that's better than just return void. I think it's better because the branches that kind of just die, you kind of don't want to modify anything. You don't really want to return any values, because then you got to figure out how do you return a value but also denote that that value should be ignored. You can maybe return a Boolean, I guess, like a true or false. but that doesn't really matter that much. Don't necessarily need that because you're gonna be modifying your values as you go anyway. So yeah, so you check the left subtree, check the so that's the those are the two, those are the base cases, and then you recurse on the left subtree, recurse on the right subtree. After recursing on the left subtree, two return values you should get is you might get an index. Actually, yeah, let's return true or false, right? Because if we get a true, then we should kind of terminate early with a true, and then and actually kind of push that upwards. If we return false, we should also terminate early. So there should be kind of this. Yeah, I think it's good to do return a true or false, and then the values that we get, we'll return those. So like if the left subtree returns true, then we're just kind of done. We don't need to check the right subtree. If the left subtree returns false, then we want to take the values that we retrieved, which would just really be the index wouldn't be changed at all, but the in other words, the result index wouldn't be changed at all, but the number of nodes that we saw to the left, that number, that would be changed, that would be modified from the left subtree, so we get some number from the left subtree if it's not there. And now when we go on the right subtree, we have that number to check against and or to use in our checks, and yeah, I guess return a true or false, return a true or false on the right subtree as well. And the right, if it's not on the left, if the left subtree is false, then the right subtree could also be false. And in which case we would return false for both. So it's going to be an OR of the left subtree and the right subtree's return values. And we would terminate early if we have a true on the left subtree. Yeah, we wouldn't even bother to check the right subtree. Yeah, I mean, that doesn't matter that much. Because you end up doing, well, actually, it does. Actually, it does. There is actually a terminate early too, again, if the, so if, yeah, the reason you want to, yeah, you definitely, yeah, okay, because we want this to be logarithmic time, right? So our terminating early is kind of important, actually. We don't want to just visit every single node. The left subtree, or just the node in general. If you have too many, if your minimum value is larger than the height, than h, greater than or equal to h, and you have too many nodes, then that's actually, you want to recurse on that, on the left side. If the minimum value is larger and you have not enough nodes, then you don't need to recurse. You can return right there on that node. You can set, you can return true. Excuse me, it's a false, but you can immediately return there. That's what makes this logarithmic. Is there is that early termination where there aren't enough nodes on the left side, and Yeah, so you just return. Also, if there aren't enough nodes, now, assuming that's a left subtree, right? It could be a right subtree where the total number of nodes is insufficient, and you would return the same logic, right? Yeah. Interesting. Just thinking if that makes any sense, if that works. If you look at a right leaf or something, you would return false very quickly, or even a right subtree, but not a whole, just part of a right subtree. You know that including everything to the left that we saw and including that subtree, still not enough. The whole subtree. Then now what's interesting is that's if the height is small is the height is greater than or equal to h. What if the height is less than h, the minimum height, but also, or just if the height is just less than h, the minimum height, then you may be in a position where some of those nodes are greater than the height, and you want to calculate, you want to add, you want to get all of those, still want to add all those up. For that particular subtree. It's kind of what you're doing, is you're kind of like also along the way calculating, oh my ear. Ouch. Excuse me. Oh, my ear. Ugh. Got something of an earache. Also calculating, yeah, you're calculating sort of as you go, calculating the number of nodes that you've seen that have at least that particular height. You're trying to do that efficiently. Yeah, if you see a node and the height is less than, that's a node you recurse on, just like the head node. You would recurse on that node, and you'd operate on the left subtree and the right subtree. And what would you do with that node? That node, you wouldn't actually do anything, I think, right? You just keep going, because you'd actually, yeah, you'd return the left and the right subtree results, right? It's kind of what you do. You end up just passing through that node, basically, and you'll end up with a certain sum of however many nodes are of that particular height in that subtree, and either true or false, meaning you'll accumulate the number of nodes of that height in that subtree, ideally, and then you'll also get an idea, either a true or a false there. And that should be logarithmic overall. I think so. I think it is. Pretty sure it is. I think the whole algorithm ends up being logarithmic, but it's definitely a quite the algorithm, quite the thing, because you're kind of doing a bunch of things at the same time. You're counting how many nodes in that subtree has a height of at least h, and you're going to return the index where you should place this node if you want all of the nodes to the left of that node, of that spot, to be equal to of that height. That all the number of nodes to the left of that spot that are at least height h to be equal to k. So you're gonna have that index. So that true and false boolean that we return can tell you whether or not we found that index, basically. Yeah, it's a mouthful. That's quite. I think we could do that in logarithmic time, as stated. So I think we can find an index. Now the tricky thing is now the last question we have is, okay, we can do the updates and the swapping relatively easily, do that in logarithmic time. We can build our interval tree in nlog n time. We can even, given a particular h and k pair, find where in the tree we would want to put that h and k pair in order to have the right number of nodes, given the current structure, the right number of nodes to the left that have that that property that there's at least there's exactly k nodes to the left that have at least height h. Okay, we can do those things. However, the problem we have is once we found the right position for our node in the tree, then we would swap the index that we're looking at with that node, update our interval tree, which again we said logarithmic time to do that, and then we would say, okay, but is the node that we're looking at now, is this node in the right spot, right? And then we said that query is efficient with an interval tree that's updated properly, so that's logarithmic time. So now we do that, check. And now the question is, if it's not still in the right spot, we've got to do that operation again, where we find where in the tree now, our new tree, or now our updated tree, where should that go in the tree? And repeat. You can repeat this over and over, keep swapping and sort of putting values in the right spots until the value you're looking at is in the correct spot. However, there are a few problems here. Like, one problem is we don't know how many times we're going to have to call these things. And the other problem is not only do we not know how many times we're going to have to make all these calls, but when we're swapping things around, we may have actually invalidated our previous positions. Like, in other words, the nodes that we had swapped around before, they might not be correct anymore. They might not be in the right spots. So we don't actually know if that's even, if we may need to go back again through the whole array after doing all of these manipulations. That's a really interesting question. Because the reality is that any swapping you do is going to cause there are other nodes that are not in the right spot, and if the correctness of where their position relies on the positioning of the other nodes, then when you move a node, these other nodes that seem to be in the right spot might no longer be in the right spot, which is so confusing, I realize. Yeah. At first glance, this seems to be very similar to a sorting problem in that every node has like sort of a true position that it should be in. However, that true position is somewhat relative to the other positions. So to bring this back to the bubble sort, yeah, I mean you can at least perform bubble sort in n squared log n time, but that doesn't seem particularly efficient. But it does give you this sense of like, well, if you could bubble sort in n squared log n time, what about regular sorting, which would be like n log n, and then I guess it would be n log squared of n, because you have an extra logarithmic kind of overhead for manipulating your elements, checking the conditions on the elements. I don't know, actually. It's a really interesting question, though. I guess I could see why it has so many upvotes. It's a really challenging question. But I think that's an n squared log n solution that I just came up with, like a bubble sort using that interval tree that I described, where you could perform those queries. You don't necessarily need to find out exactly where it should go. You could just swap it, and you'll have kind of a bubbling up of the elements into their correct positions, which I think eventually will get the correct solution n squared log n time. I think that's true. I think you can do it that way. So that's at least a solution that's better than exponential time. However, not necessarily what we're looking for, I guess. This makes me think of if you recall that there was a question that was a Eulerian path. I think we had to visit every directed edge in a graph. In this case, it's a Hamiltonian path, but it's got to be the correct it's a Hamiltonian path in a complete graph where every node could have any other node next to it, and it's a Hamiltonian path that has certain conditions. So some of these paths are not possible. Yeah. Challenging question, man. Definitely. Excuse me, a challenging question. Hamiltonian path with certain conditions. No, Hamiltonian paths are NP complete to begin with, so, or NP to begin with. So I was finding those paths, so let's not get into that. Let's not do that. That'll be a bit much. Okay, well, what were we looking for? Which we were thinking before? Yeah, okay, bubble sort seems to work. So what are some alternatives to bubble sort that are efficient? Well, there's divide and conquer algorithm. Merge sort, I guess. We can maybe try that. There's quick sort, which technically should do the trick. Quick sort, merge sort, or n log n. Right, quick sort if it's intro select, or intro sort rather, would be n log n. There's heap sort. That would be see, the problem with any of those algorithms is you're not there's a total order on the integers in the sense that or elements, like you have certain ordering on elements basically is transitive, if that makes sense. Whereas this property for these elements, it kind of changes depending on what elements are already in the queue to the left side, if that makes any sense. It's not a priority queue. You could say it's like a priority queue, but it's not really a priority queue. Well, actually, no. No, priority queue is a little bit different. Priority queue is basically a heap. Actually, no, I don't even know how do priority queues even work. I wonder if this is just a priority queue. I don't think so. No, I don't think so. I don't think it's too simple to just be a priority queue. We can go look up and research priority queues though, just to be certain that that's unrelated. It's maybe not a bad idea. Something we'll consider. But the thing that I'm thinking about here is what thing that I'm thinking about, the thing that I'm pondering is what is I gotta really think about this, huh? Excuse me. Missing some things here. Yeah, the ordering for these elements is different. Kind of need to define an ordering. Maybe you could, if you could define an ordering. Could incorporate that interval tree. So, okay. All right. So if we did like a merge sort, right? You have two elements. In the base case, you have two elements. You're going to compare the two of them. You can use the interval tree. And I guess what you would say is, if, depending on what the interval tree looks like right now, if one of these elements is in the correct spot, then don't move these two elements, I guess? No, I wouldn't say that. I would say if either of them are in the wrong spot, then you want to swap them. Yeah, the thing that the reason why the merge sort doesn't really work nicely or correctly with this algorithm, I guess, with this approach, is that this condition of like, okay, let's say single elements, if you broke this problem down into arrays of single elements, they're sort of not, some of these elements can't be in the right spot, right? Because they only have one, there's only one element, so the ones that are expecting elements to be to the left can't be true. So there's like an issue of like sub problems not really working correctly. You kind of have to have a reference back to like what the total tree looks like. What are these indices that you're looking at, and what is the total tree? The total interval tree, what the current array setup look like, and okay, I guess you could perform some swapping. But let's say, like, the only thing you really can do is say, if both of these elements are in reasonable spots, then leave them. Really, you would do. It's not really clear what you would do. If they're both not in the right spot, then I guess you just don't do anything. If they're both in the right spot, then leave it. If one of them is in the right spot, one of them isn't, I guess you just leave it too, because what are you supposed to do? And then, okay, then now you have two arrays of size 2, right, as the next step. Right, we're just assuming for a moment that the number of elements is a perfect power of 2. We've got all these different steps in between where we're swapping and combining these arrays. I guess we could use logic like that. But then the next step above, we would say we have these two arrays of size 2, and if any of the elements are in the wrong spots, then we probably want to do something. Let's say, well, if any of the elements are in the right spots, then we want to leave them. But if they're in the wrong spots, we want to do some kind of a swapping, I guess. And I guess there's a merge that you do also, merging into another array. That's really the crux of the algorithm. It's you only really do the swapping when you're dealing with merge sort. You really merge two sorted lists is like most of the algorithm, and then you only do this quote-unquote swap really is a merge of just two elements. So how do you merge these two quote-unquote sorted? Because they're not really sorted. I mean, you can kind of pseudo sort them in that you want would want the element, you would want to be as close to correct as you could be, I guess. So the element that has a k value that's non-zero, you'd want that to be to the right, and the furthest to the right. So I guess you would probably merge by, and the element that doesn't have a k value, you want that sort of to be to the left, or has a small k value for that to be to the left. When you merge these things, though, it's not obvious. What's interesting is that in terms of like sub problems or subroutines, the sort of the value at the ith position in the queue, if you have considered all the elements to the left are in the correct spot, then you can find sort of that ith most element, right? That's got to be among the elements to the right. The tricky thing though is how do you figure out which element is supposed to be the first element on the left, and then which one's supposed to be the second one, and which one's supposed to be the third one, et cetera, et cetera. Right? You sort of can solve this problem incrementally in theory, but it's kind of challenging, isn't it? Yeah. Huh. Because there are multiple choices for the first value, right? 3, 4, 5. You have 3, 0, 4, 0, 5, 0. I think the example we had, second example, had 4, 0, 5, 0, and 6, 0 in the array. Turns out I think 4, 0 is the correct value. To pick. Then you could pick 4, 5, 0, or 6, 0, or probably so few others. And so you have a few different possible choices that actually could go there. So the tricky thing is that you would eliminate, of the values that could come first, or of the values that could be in position I, even if you've resolved all of the I minus 1 positions, all of the positions less than I. There's still a lot of different options you could pick, and not all of them are correct. In fact, there's probably only one that's correct. I think that's part of the trouble. It's part of the reason why the exponential time algorithm doesn't really work that nicely. It's because there are a lot of possibilities that you end up working through. Really interesting question, I have to say. Take that set off for a minute, just kind of continue to ponder. So I've been thinking about this problem for a while now. I'm thinking I'll take a break because, yeah, I don't know. I kind of fell asleep too. Thinking about it, nodded off, and I'm not coming up with any solutions here, man. I don't think the interval tree solution will actually be correct. I don't know, man. I don't know. I don't know. I think I gotta think about this problem a bit longer. I want to say that there is a slightly better solution. There's got to be. It's just, I don't know. I don't see it. Yeah, it's the bubble sorting as I described. I think that's a solution. So that's quadratic. It's n squared log n, but it really is inefficient in the sense that with 2,000 elements, it's kind of expensive to do it that way. And not to mention, like, it's kind of a lot of coding too. Like, you gotta get an interval tree, and then you gotta code the updates correctly, and you also gotta code the query, the updates, and then the index query as well. Like Boolean true or false if the condition holds, and then also a check for if the like if it's in the right spot, right? That's that query, and the other query is finding an index for that value based off the interval tree, and then finding the other two things. The other thing to do is the update, and then you can do a bubble sort where you just kind of do a loop from left to right, checking two value, checking is this value in the correct spot, or yeah, I guess it would be every second element, we'll say, or I don't know, starting from the second element all the way to the right, you just say if this is in the right spot, leave it, otherwise swap it with the element to the left, and you can perform those two updates to the interval tree accordingly. And that's kind of it. And you would do that bubbling routine as many times. You keep repeating that over and over until every element is in the right spot, and you're done. And yeah, they'll kind of eventually find themselves in the right positions. But this is a kind of a sorting algorithm. It's sorting. Yes, it's a sorting question. It's just a weird sorting question, I guess. The sort that you're looking for is special. It's not the typical kind of a sort, the ordering. It's a slightly different order, where there are multiple possible values. Multiple possible values, multiple possible solutions. It's just a different kind of a sort, I guess. I don't know. It is a sorting related question, but it's a different kind of a sort. I'm not really able to, at the moment, I'm struggling to kind of wrap my head around it. I don't know, man. I don't know. I guess it's a good question. Let me do this. Let me take a break. Come back to this later. We'll make this a part one. Then, I don't know. I gotta keep thinking about it. I didn't really do very much programming as much as didn't do much programming on this problem as I did just kind of thinking about it, because yeah, man, I didn't come up with a better solution than the one. I didn't come up with a better solution than the one. A friend called and texted. I should respond to him. I didn't come up with a better solution than the one I just described. Like using an interval tree is great, but it doesn't solve the problem, I think, efficiently enough. 40 million sort of operations
which is kind of what we're looking at if we did n squared log n of 2000. That's kind of a little bit yeah, 40 million operations is kind of a lot. It's kind of a lot. Like that probably will not be efficient enough for this problem. That's 10 to the 7th. Yeah. You need a little bit more efficient than that for this to work like quickly. Probably not the timeout. I could try coding it and then submitting it and just see if we time out or not. I think it times out n squared log n time using the bubble sort using an interval tree. It's a solution, but it's not good enough, I think. So let me come back to this. Let me say for now, bubble sort with an interval tree using an interval tree will solve the problem, but it won't be efficient enough. It provides a solution. Let me go make this a part 1. And I'm gonna keep thinking about this though. I'm kind of stumped. I kind of feel like I need a break. Just like I also want to go use the bathroom. But yeah, I didn't really. Yeah, let's see how many. 2 hours. Yeah, 2 hours thinking about this. I think it's okay. We can take a break. Make this part 1. We'll have part 2. Part 2. I guess we'll think more about what we could do. I don't know, man. I really think I don't have a solution. You know, I don't want to look up the solution either. I'm tempted to because we've already spent like 5 hours on this problem. It's like kind of a lot of time if you don't know the solution. Sometimes it's better to just like look up the answer because who knows how long it'll take you. You don't really want to waste time. I guess I don't know. That's another question too. Is like how much time should we be spending on all of this stuff to begin with, right? Like, what does it all really matter anyway? Maybe I should just be spending all my time reading the Bible and just everything else. Don't worry about it. I don't know. All right. Let me go. So talk to you soon. Thanks for watching. Take care.